Hey everyone, welcome to Insights by Rish. In this video, we will cover a linear regression project, which is house price prediction. In this project, we have a house price prediction dataset, and based upon which we are building a linear regression model that will predict the prices of the house depending upon the input data, which we are feeding the model during the training process. So before beginning with the coding part, we'll understand the dataset. This is the dataset of house price prediction. And the last column which we have here, which is the sales price, we have to predict this. So this is our target column, MS subclass. Now the MS subclass, this particular column stands for the number of flats in a building. A building consists of n number of flats. These values are the number of flats that a building consists of. The next column, which is MS zoning, stands for the residential density. RL stands for residential low density, which means the houses that can accommodate only a single family, like row house. RM stands for residential medium density, which means apartments or flats that can accommodate more than one family. RH is a category which stands for residential high density, which means it consists of commercial and industrial shops or stores. The next column is lot area. Now lot area stands for the area of land or the size of land on which the property is built in square feet. So this is the square feet of the property. Next is lot config. Lot config stands for the layout or shape of your property, which means whether it's a corner plot, whether it's an inside regular subdivision plot, or FR2. The FR2 stands for when it has road frontage on two sides. Building type consists of whether the building can accommodate one family, two family, whether it's a duplex or a twin house. The next column is overall condition, which means how much old the property is. The next column is year built. These are the years in which the property was built. The next column is year remodification add, which means whether you have performed any remodification on the building. That includes increasing the size of your property or making some extra subdivisions inside the plot or some kind of remodifications. So if you have performed any remodifications on the property, then that particular year will come under this column. The next column is exterior first, which means the exterior part of your building or the outer part of your building is covered with what material, whether it's some metal, whether it's a plywood or etc. The next column consists of basement size in square feet. And the next column, which is the L column, consists of total basement square feet. And the last column, which is sales price, you have to predict that. This is the historical data which will feed our model for training purpose, and then while predicting you need to input all these values and then your model will predict the sales price. So we will be implementing linear regression algorithm here and some regularization techniques. Let's begin with coding. We'll import the pandas library. Next we will import warnings, which we require because the Jupyter notebook gives a lot of warnings whenever you import a library and use the fit method on that. Next thing we are going to do is we will be loading this dataset into a data frame df. So df is our variable of data frame type into which we are going to load this Excel file. Now one thing you need to keep in mind, though this file is an Excel format, we have downloaded it and stored it on the system in CSV format. This is the path on which the CSV file was stored. Let's check the shape of data frame. This means that our dataset consists of 2919 rows and 13 columns. Let's display the dataset. Here we are displaying only first 3 rows of the dataset using the head function. Now by looking at this dataset, first we need to perform the data cleaning task and data pre-processing task. Let us check for duplicates and drop the duplicates if there are any. Now here you can see initially the number of rows and columns were 2919 rows and 13 columns, and even after dropping the duplicates the number remains same, which means there were no duplicates present in our dataset. Moving ahead, we'll drop the unwanted columns. While looking at this dataset, you can analyze that the ID column is not necessary for your model prediction. it do not provide any meaningful information. So we'll delete this column which is unwanted to us. Let's display it again. This ID column is now not present in our dataset, so we have successfully deleted that. Now in place true plays a very important role here. If you don't mention in place true, then these changes would be made temporarily, which means it would be shown only into that particular instance when you display that. While when you rerun that same query, you won't find that changes made into your dataset. That's because when you don't mention in place is equal to true, it makes your changes temporarily. But if you want to make the changes permanently, then you need to include in place is equal to true. Now, the next thing we'll do is we'll check for null values. Now we have used isNA function, which is used for checking the null values, and we have used the sum function along with that to check the count of null values. We don't want to check the null values into a single row and single column. We just want to take the count of null values in a particular column. So we can see there are some null values present in MS zoning, then exterior first, basement square feet, total basement square feet, which are comparatively very low as compared to the sales price. It consists of very large number of null values, which are 1459, and sales price is our target column. So a target column can never consist of null values because it will affect the performance of our model. First thing we'll do is to handle this null values, we'll replace it with something. Now there are multiple techniques by which you can replace the null values. We will use the imputation method with mean strategy, which means we'll take the mean of sales price column and fill that null values with that particular mean value. We'll do that using simple imputer from sklearn. As we can see here, I've imported the simple imputer model from sklearn impute class. This imputer is an object of simple imputer class, and I've included the strategy mean, which means I'm replacing the null values with the mean of that column, and then we have fitted that imputer into the sales price column. One more important thing is I have mentioned two double square brackets here. This consists of double square brackets, and the reason is if you include only a single square bracket, then that will consider it as a series data frame, while the imputer function can only work on data frame data type. And the pandas, as you know, the pandas consist of two main important data types, which are series and data frame. Imputer only works on data frame and not on series, but when you include only a single square bracket here, then that considers it as a series and not a data frame. That's why to make that a data frame, we include two square brackets. Our imputer function has been successfully created. Next, we'll transform it. Let's check the mean of that sales price column. This 1,80,921 is the mean of sales price column, which means the mean or the average sales price is 1,80,921. And what this imputer will do, it will replace all the null values from the sales price column with this value, 1,80,921. Let's transform it. Now when you will check the count of null values, here we can see the null values in the sales price columns are now 0, which means we have successfully handled the null values from sales price column. Now apart from this, there are some very few number of null values in other columns as well, and we'll replace that with 0 because that's not a very important column for us. The very important column for us was sales price, and we handled that column in a better way. Apart from that, all the other columns which consist of very less number of null values will replace it with 0. As we can see, now all the null values are being handled successfully. So we are done with the data cleaning part. The next thing we are going to do is we'll use the describe function on this dataset. Here we can see the statistics for this dataset, and when you look at this lot area column, you can see something unusual, which is for the 75% of data comes under 11,570, but the maximum value is 2,15,245. There's a huge difference between the 75% of data and the maximum value, which means we can easily conclude that the lot area consists of outliers, and we need to handle this outliers. So first, to look at the outliers, we'll plot a box plot. The box plot is a plot from Seaborn that helps us to analyze the outliers. So let us plot that. Now we'll set the background for the plot, which my personal favorite is dark gray. You can even keep it white. After plotting the box plot for the lot area column, we can see it consists of numerous outliers. The box plot is actually from the upper fence up to the lower fence, and except that, all other data points which are represented using this circle are your outliers. The next task then we'll do is to handle these outliers. Now there are multiple methods to handle outliers. We can have IQR method, that is the interquartile range. We have Z-square method, standard deviation method, and the percentile method. But the most appropriate one, by my perspective, is the interquartile range method, IQR. And we'll use that in this code. For that, we need to import the NumPy library. Next, we will compute the quartile 1 and quartile 3. As we know, the quartile 1 only covers the first 25% of data, which is this. That's why we have mentioned 25 here, while the quartile 3 covers 75% of data. Here we have computed quartile 1 and quartile 3. Now we'll substitute that in the IQR formula, and the formula for IQR is quartile 3 minus quartile 1. After computing IQR, the next thing we have to do is we have to set some threshold, lower bound and upper bound. For doing so, we cannot randomly set the values for lower bound and upper bound as we do in Z-score and standard deviation methods. Here we have formula to do so. These are the formulas for lower bound and upper bound. Lower bound is the lowest threshold that we have, that anything below that threshold will be considered as outlier, while upper bound is the maximum threshold, which means anything above that upper bound will be considered as an outlier. Now we'll create another data frame in which we will only include the instances that consist of data values between this lower bound and upper bound. Now we can see here in this particular line, what we have done is we have only included the instances from the previous data frame that consist of your lot area value lesser than your upper bound and greater than your lower bound, which means the data value of lot area which falls between these two thresholds. Now when you check the shape of your data frame, it consists of 2550 rows. Initially it was consisting of 2919 rows, and now it is consisting of 2550 rows. That means around 400 rows have been removed. This means we have handled the outliers successfully. The next thing we are going to do is we'll check the data type of all the columns from the dataset. In this we can see the int denotes the integer data type while the object denotes the string data type. Now when you look at the dataset, you can find that some column consists of numerical values and some column consists of categorical values. In a machine learning model, you cannot feed a categorical value column to the model for doing prediction, because the machine learning model cannot handle categorical values. It can only deal with numerical values. For that purpose, you need to convert your categorical values into the numerical ones, and you don't need to do that manually. You have libraries in order to do that. The MS zoning column, the lot config column, the building type column, all this consists of categorical values, and the next task we have to do is to convert these categorical values into numeric ones. So I'm creating a variable categorical column. This will include a list of all the columns consisting of object data type. As you can see, the categorical column variable is consisting of all the columns which are having object as data type, which means all these columns are categorical in nature, and the thing we have to do is we need to convert them into the numeric ones. Now to handle this categorical values and to convert it into numerical ones, we will include one hot encoder module from sklearn preprocessing library. Let us understand this. So one-hot encoder is a module from sklearn preprocessing library, and encoder is an object of one-hot encoder class. Sparse is equal to false means we are not dealing with any sparse arrays. We will be dealing with dense arrays. And handle unknown is equal to ignore, which means if you come across any unknown value which doesn't usually fall in the standard categorical nature, then you will ignore that. Next thing we are going to do is we'll use the fit function. What we have done here, we have included the list of all categorical columns from the data frame, and we have performed the encoder operation on that. So this will create new columns which will consist of numerical values. Now what one-hot encoder does, it converts your categorical values into numerical ones, but in the form of zeros and ones. Let us understand how it converts your values into zeros and ones. Let us consider that you have a hobby column, and in that hobby column you have some categorical values, like the first hobby that you have is to draw, the next hobby that you have is music, and the third hobby that you have is swimming. Now you want to convert this data into the numerical one using the one-hot encoder. What the one-hot encoder does is it creates new columns for all these values. What it will do is it will create one column for draw, another column for music, and third column for swimming. Then it will assign the values in the form of zeros and ones. Like for the first instance where the hobby is draw, then in that case it will assign 1 for draw and 0 for remaining. In second instance, when the hobby is music, it will assign 1 to the music and 0 to remaining. In third case, when the hobby is swim, it will assign value 1 to swim and 0 to others. In this way, the one-hot encoder is converting your categorical column into numeric ones. But it also increases the dimensions of your dataset. Initially, we had only one column, but now that we have performed one-hot encoder on that, it now consists of 3 separate columns. By looking at these columns, you can easily analyze that in the first row where the value is 1, then that is the hobby. While in the second instance, wherever the value is 1, that is the hobby. So the one-hot encoder, it converts your categorical values into numerical ones in the form of zeros and ones. So moving back to the coding part. As you can see here, we have successfully created the encoder class. The next thing we have to do is we need to create new column names. As we can see here, new columns are created. This new column names draw, music, and swim are given by us. But we can only give it manually when we have very less number of columns. Like here we had only 3 columns. That's why we have given that names manually. But what if we have n number of new columns? Consider that if we have 10 hobbies here, in that case 10 new columns will be formed by the one-hot encoder class. In that case, you need to give 10 new column names manually to all the 10 columns, which is a very time-consuming job. Now, in order to prevent doing that manually, you will use getFeatureNamesOut function of the one-hot encoder library, creating a variable encoded columns. What we are doing here is we have created new column names and we have stored that in the encoded underscore columns variable. We have used the getFeatureNamesOut function from the one-hot encoder class, which extracts the names of features along with their attributes and creates a new column name. Which means in the MS zoning feature, we had 3 categories: RL, which is residential low density, RM, which is residential medium density, and RH, residential high density. So what it did, it extracted the attributes, it extracted the categorical attributes and preceded it with the feature name. So this all are the new column names for your new numerical columns that you are going to create. Let's display it. We are just transforming the data in this particular line and storing it in the new columns, encoded columns, which are this particular columns. So we are storing the new transform data under this column names. Now when you look at the data set, you can find this new data or the new columns added to your data set, which are in the form of zeros and ones. Now that we have added the numerical ones, we can delete the categorical columns from the dataset, which we don't require anymore. Let's do that. Here we have dropped the categorical columns. Now when you check the dataset, now you have all the numerical values. You don't have any categorical value present here. Now let's divide this dataset. The next task that we are going to do is we are going to divide this dataset into the input features and the target variable. From all this, let's display the columns first. So from all these columns, sales price is the only column that we want to predict, which is our target variable. Apart from that, all other columns are your input features that you are going to feed your model. So we'll divide the dataset according to that. In this particular line, what we have done is X consists of all the input features. So we had just dropped the sales price column, and apart from that we have included all the columns in the X variable, which means that are our input features, while the sale price column is our target variable and we have included that in the Y variable. Now looking at the input data frame, the X data frame, we can find that every data here is on a different scale. When you check the MS subclass, it consists of different scale. By scale, what I mean is the minimum value and the maximum value. When you compare, in every feature you have a different minimum and maximum value, which means all the columns are on different scale. The MS subclass or the maximum value is in hundreds, while in the lot area the maximum value is in thousands. So every column is on a different scale, and the next thing we have to do is we need to bring all these columns onto one standard scale, and we'll be doing that using the min-max scalar library from the sklearn. Here we have imported the min-max scalar module from the sklearn preprocessing library, and scalar is the object of our min-max scalar class. Then we have used the fit function and we have provided the input dataset, that is X, to our scalar object. Let's transform it. Okay, so here in this line we have transformed the dataset. Now the main reason behind using this square brackets and a colon here is, if you won't give it here, then your entire transform data will be stored in the format of an array. But you wanted your transform data to be stored in the format of a data frame, that is in the form of rows and columns. That's why it is necessary to provide a square bracket with a colon here. Now when you look at the dataset, you can find that all the columns are now on a single scale, that is between 0 to 1. What this min-max scalar does, it converts your data into some value which is between 0 to 1. So the maximum limit is 1 and the minimum limit is 0. This process is also called as data standardization process or data normalization process. The next task we need to do is to divide this dataset into the training and testing set. When you have a single dataset, from the same dataset you need to use some portion of the dataset for the training purpose, that is to train your model, and some portion of the dataset to test your model. So for that you need to divide your dataset, and you don't do that manually. You use the train test split function from sklearn model selection library. In this line, what we have done is we have splitted the data with 8:2 proportion, which means the test size 0.2 means 80% of data is included in the training set, while 20% of the data is included in the testing set. And random state is equal to 42, which means we want the same number of rows to be included in the training set and testing set every time when we run this code. If you don't apply this particular random state is equal to 42 element, then in that case, whenever you will run this particular code, every time you will get different rows in training set and the testing set, which means every time the accuracy of your model will change. Now let us check the shape. So we had some 5500 rows, and from that 2400 rows are in training set and 510 rows are in testing set. Let us understand how this train test split is working. Let's say you have a data set like this, and it consists of input features x1, x2, x3, and y is our target variable. Now in this case, the whole data is our input and this feature is our target one. Assume that there are some 10 rows in this data set. 10 rows in this data set. When you perform the train test split with the proportion 0.2, which means 80% of data in the training set and 20% of the data in the testing set, what it does, it divides your entire data set into two parts. One is your training set and the next is your testing set. So 80% of the data is included in the training set, which means 8 rows are included in the training set. 8 rows are included in the training set. That is, you will use 8 rows of data to train your model, while 2 rows are used in testing set. That is, you will use 2 rows of your data to test the trained model. So in this way, you are dividing your data set into train and test model. You can also divide your data into the validation set, which means the training set is used to train the model. The validation set is used to test the model during the training process. And the test set is used to test the model after the training process has been completed. But generally, we just divided it into the train and test set and not the validation set. So as we can see here, initially we had 5,500 rows, something like that. And now we have 2040 rows in training set and 510 rows in the testing set. The next thing now we will do is an important part and the main core concept of our video, which is we'll train the linear regression model. So for that, we will import the linear regression module from the sklearn library. We will create an object of linear regression class. Model is the object of our linear regression class. We will use the fit method. We will fit the training sets here, that is the X training and Y training. So now we have fitted our training set X train and Y train here. The next thing we have to do, we are going to do some predictions. Let's say we are storing all our prediction values in some ypred variable. Ypred, this is a variable in which we will be storing our prediction values. We will pass the X test dataset to do the predictions, and we want to predict the values for Y test. Now, the original values for Y test are this. These are the values for your original Y test. Let's display only the first 5 values. So these are the original first 5 values for your Y test. And now let's check what our model is predicting that. Original value was 2,26,000 and our model predicted it to be 2,05,000. Original value here was 2,90,000. Our model predicted it to be 2,02,500. Here the original value was 1,80,000. Our model predicted it to be 1,74,000. So the predictions are close. Let's evaluate the model. Now that we have trained our model, the predictions are somewhere close. We can't get the exact prediction because in that case our model will overfit, which means the model has memorized the data and it hasn't learned any patterns from the data. It is not using the basic logic behind building the patterns and then evaluating the model. Rather, it is memorizing all the data and just copy pasting the outputs and results. So that's an overfitting condition, and when you will start getting the exact values for the testing and the prediction set, in that case you can come to a conclusion that your model is overfitting, and that's not a good condition. Neither your model should underfit nor it should overfit. It should be somewhere in between. Let us evaluate the model. If you have seen my previous video, in that video I have shown multiple evaluation metrics for linear regression, and we will use one of them, which is mean absolute error. Now this mean absolute error, we have imported it from the sklearn metrics library, and we will pass the original values and the predicted values in this function. It will evaluate then the difference between that and how good the model has performed. So let's pass the original values, which are Y test, and the predicted values, which are ypred. So 29,949, currently this is the mean absolute error. Now the next step is, now that we have evaluated the model using the mean absolute error, we will try to do some regularization techniques, some optimization techniques in order to reduce the mean absolute error. Our ultimate goal is to lower the value of mean absolute error, and for that we will do regularization. We will perform L1 regularization, which is the Lasso regularization, and L2 regularization, which is the ridge regression or ridge regularization. So let us start with the L1 regularization or Lasso regularization. We will import the Lasso module from sklearn library. We will create a Lasso model for it. This alpha is equal to 50. Alpha is a hyperparameter. Hyperparameter is a parameter onto which our model depends. As we change that parameter, the performance of model also changes. Such kind of parameter is called as hyperparameter. Here alpha is our parameter, and the value of this alpha 50 is on the trial and error basis. There's no any standard value for alpha. You need to do some trial and error. You need to do some grid search techniques, cross-fold validation techniques, and find the perfect value of alpha for your model. Max iterations is the number of iterations the Lasso model should perform in order to perform the regularization, and this stands for tolerization. So here the tolerization, or here the tolerance, and this stands for tolerance. Here your tolerance is 0.1. It is 1% tolerance. Let's fit the training set in the Lasso model. Now let's evaluate the Lasso model using the mean absolute error. So here we'll store the predicted values in the Lasso pred variable. This Lasso pred variable will store the predicted values of the Lasso model. Let us evaluate the model now using the mean absolute error. Here we will pass the original data values, which is y-test, and the predicted one, which are now the Lasso pred. So as we can see, there is some slight reduction in the mean absolute error value. Initially it was 29,949, and now it has been reduced to 29,916. So there's some slight reduction, which means L1 regularization is doing better than the normal linear regression module. Let us try performing L2 regularization, which is the ridge regression. Here, similar to Lasso regression, we have provided the alpha, which is our hyperparameter, and again it is dependent on trial and error basis, the max iteration and the tolerance. We have fitted the ridge model on the training set. Now let's store the predicted values of the ridge model in the ridge pred variable. Again, we will evaluate it using the mean absolute error. We will provide the original data values, which is the y-test, and the predicted data values now in this case are ridge pred. Again, there is a slight increase in the mean absolute error value. Initially, using the pure linear regression algorithm, it was 29,949. Then when we used Lasso regression, it got reduced to 29,916. And then when we used ridge regression algorithm, it again increased a bit. Then after all this evaluation, we can come to a conclusion that L1 regularization is doing much better than the pure linear regression model and the L2 regression. So this was the house price prediction project using the linear regression supervised machine learning algorithm. That's it for the video. Thank you for watching.